Good afternoon and welcome. Art of Java type patterns. We're going to be talking all about pattern matching in Java and the new features that we have in the Java language. We've got JDK 19 that got released just recently, and so there's been a lot of changes over the last few versions, and we'll go through all of those things and how you can use those in terms of your code. Now, I realized when I was putting this presentation together that there's actually a lot of code on my slides, and I thought to myself, maybe I should actually do this as a live coding experience. And then I thought, no, the audience really won't appreciate that, because despite having been writing code for 45 years, my typing is rubbish. And in front of an audience, it's even worse. So I figure it's actually much easier if I just put the code up on the slides and then I can talk about it rather than you having to deal with me trying to type. So what are we going to talk about? Well, we could talk about pattern matching in Java. And if you look at the APIs that we have java.util.regex. And that's been there since JDK 1.4. And we could write some code with that, and we could say, let's create ourselves a pattern. And we will create a pattern which will match against something which is A followed by 0 or more characters followed by a B. And then we can generate a matcher using that pattern and say that we want to match against this particular string which has some A's and a B in it. And then we'll actually call the matches on that to see whether we actually get a match. Great. And if we really want to, we could do that in a single line of code. Wonderful. Now, it's interesting because I did this presentation as a webinar a few weeks ago. And I noticed that at this point, 2 of the people on my webinar dropped off. And I thought, okay, that was a little unfortunate, because had they stayed for just a few more seconds, they would have realized this is not what we're here to talk about today. No, we're actually going to be talking about language level patterns. So don't worry, I'm not going to go through regular expressions and how that all works. So what do we mean by pattern matching in terms of the language? Well, pattern matching's been around for a long time. In fact, if you look at programming languages right back to the 1960s, they've had pattern matching in them. You know, if you look at languages like Haskell and even languages like Awk. Who here has used Awk? Okay, good. That's what I like to see, because it's a good piece of technology. So it's been around for a while. And if we look at what we actually mean by a pattern in this context, what we're dealing with is 2 things. The first is a match predicate. And in this case, what we're doing is putting something there which we need to determine whether we match against a given pattern. So predicate is where we say, does it match or does it not match? It's a Boolean type of thing. And so we've got a target that we want to match against, and we have our predicate. And then associated with that, we have some pattern variables. And strictly speaking, you could say it's 0 or more pattern variables, which are then conditionally extracted if our pattern matches against the predicate and the target. So this is essentially what we're dealing with in terms of pattern. And we'll see this as we go through the rest of the presentation. The next thing to understand is there are actually multiple types of patterns that we can use in terms of the language. The first of them is a constant pattern type. And if you think about it, we already have that kind of pattern in Java because we have the switch statement which has cases. A case matches against a constant because you have case 1, case 2, case 3. In that case, if you'll excuse the pun, we don't have a pattern variable because there is no variable. It's a constant. So we don't need a variable to represent that. We know that we've got a 1, we've got a 2, we've got a 3. We then have more interesting types of patterns, and the next one is obviously a type pattern, where what we're referring to is a type in terms of the Java language, i.e. a class that we want to match against, and we want to do something based on that. So we match against a type. We also have a deconstruction pattern, which is where we're going to match against the specific type, but then also simultaneously we're going to extract some information from that type. We'll see a good example of that later on as well. We have the var pattern. This also could be referred to as the any pattern in some ways. So what we're doing is we're saying, let's use type inference to get the compiler to match against something and then also map to the specific type that we want without us having to explicitly state what it is. And again, we'll see some good examples of that. And then the last one is the true any pattern, which is represented by an underscore. Essentially what we're doing here is we're saying we want to match against anything, but we want to bind to nothing, which you might think to yourself, well, what's the point of that? But we will see how that works later on. And this is sort of related to some work that was originally intended to go into earlier versions of Java, hasn't quite made it yet, which was lambda leftovers. And the idea of using an underscore where you've got a parameter in a lambda expression which isn't used in the body of the lambda expression, and so you don't really care what it is. Same thing we can do in terms of our patterns. There is actually one more type of pattern, which is method pattern, but because we don't have any examples of that, I'm not going to cover that in the presentation. So before we get into the pattern matching side of things, we need to go through a couple of features which have been added to Java recently, which tie in very tightly to pattern matching as we use it. First of those is switch expressions. Now, this was introduced because if you look at the switch statement that we've had previously in Java, very common thing, we use it a lot, but it has some drawbacks. And one of the main drawbacks of the switch statement is the fact that for each set of cases, you can put some code and then you have to remember to put a break statement in. And if you don't put a break statement in, as we all know, the logic is that it will fall through into the next set of case statements and then do whatever that does. So, as a quick survey of the audience, who here has ever forgotten to put a break statement in? Yes, you see, because I know I've done it many times. And it's one of those things that then becomes very difficult to debug your code. Actually, I tweeted about this last week because I was sitting next to my son. He's 16 and he was writing some code and he ran a test and he said, "That cannot possibly happen." And I thought to myself, how many times have I said that in my career? So anyway, well, that's one of the drawbacks. But there were some other things in terms of the way that the switch statement worked, which meant that it could be improved. And what we get is, if we look at an example of a switch statement, this is a very common usage. What we're doing here is we're switching on one particular variable, in this case day, and then we're assigning a value to another variable, number of letters. And as you can see, we've obviously got case Monday, case Friday, case Sunday, assign number of letters to be 6, and then remember to put the break statement in. The other thing that becomes a little bit sort of problematic with using the switch statement this way is that we have to remember to assign a value to the number of letters. If we've got an instance field, the compiler will give us a default value of 0, and quite happily, if we don't set a value other than that, we'll be quite happy with it. If we had a local variable, at least we might catch the error because we hadn't assigned a value. So these are things that we could tidy up, and that's how we get the switch expression, introduced in JDK 12 as a preview feature. And we can see now that we can tidy that code up by turning it from a statement which simply executes a set of instructions into an expression which executes a set of instructions but also generates a return value. Now we can assign that value once, and so we're clear that we're assigning number of letters, and we make sure we do that, and the compiler can check that we have, for every set of cases, a return value, and alternatively, if we don't have a return value, we've got an exception that's being thrown. And as you can see as well, this is really good because it makes the code tidier. There's less lines of code that we have there, and we don't lose any readability. That's the important thing. One of the reasons for that is something which I still find a little bit confusing to this day, which is that it's taken 25 years for the developers of this feature to figure out we could use a comma-separated list. So now we have case Monday, comma, Friday, comma, Sunday, rather than separate lines of code. Anyway, and then we borrowed the arrow from the lambda expression, and the right-hand side of the arrow is what we return. So this is all good. But the important thing about this is that switch expressions must be complete, meaning they must be exhaustive in terms of the values that we're looking for. We'll come back to why that's important later on when we talk about the pattern matching in this particular case. The other thing we need to talk a little bit about before we get into pattern matching is algebraic data types in Java. And there's two things that we need to talk about there. First is what we do in terms of creating simple classes in Java. We do this a lot. What we're doing is object-oriented programming. We are encapsulating some values, and in the case of a point, it is just two values, x and y, which are doubles. This is all good, and we can write a class to represent that, but we have to do a class, then we have to create two instance fields, final double x, final double y, then we have a constructor which takes two parameters, we assign the values from those parameters to the instance fields, and we need accessor methods so that we can return the values of x and values of y. 14 lines of code to create a tuple. Now, I did talk to Brian Gertz about this a while ago. I said to him, why don't we have a tuple in the Java libraries? Because, there's 4,500 public classes. Can't you just squeeze a tuple in there? And he said, well, yes, we could give you a tuple, but then you want a triple, and then you want a quadruple, and where do we stop? So they came up with a better solution to this, which is records. JDK 14 introduced the idea of a record, which is essentially a special form of class, which is a container for some data that we want to store. So it's a data type. Here, we now have one line rather than 14 lines of code. So we call it a record. We then say it's called point, and we say that the definition of that record has two values, double x and double y. All of the rest of the code that we would have had on the previous slide is created for us by the compiler. Now, because records are essentially just a special form of class, we can also make them generic if we want to. So we could have a generic type parameter t, and then we can store objects of type t in our record. We can also add more functionality to our record. We can't add extra instance fields that aren't defined in the declaration of the record. So in this case, we've got radius as a field. We couldn't add another instance field inside the body of the record, but we can have static ones. So static double pi, and we can also introduce new functionality in the form of methods, so we can have a method that calculates the area and so on. A couple of extra details about records. The base class of all records is java.lang.record, meaning that you cannot subclass a record from another class. Because it's a class, you can implement interfaces, and you can implement as many interfaces with the appropriate methods as you want. That's not an issue. Records are also implicitly final. You can make them final if you want to, but you don't have to. The compiler does that for you. They're also shallowly final in terms of the values that you store in them. So all references are final, but obviously there are things that you refer to may not be final. And one last thing about records is that they don't follow the bean pattern. This was one of those sort of contentious things that went through a lot of discussion when they were creating records, is to whether to have the accessor methods called just the name of the variable, x, or getX. And you can argue it both ways. One of the arguments is that because the values in the record are final, there's no mutator method, so there's no set method to go with the get method, so why have a get method for there? Let's just call it the value or the name of the variable. This did cause a few problems because some software relied on the idea of the bean pattern if you wanted to use data types. Things like Spring initially had some issues. They've obviously solved all that since then. But there was a workaround to that, of course, because if you just call your value getX and getY, then you will get a getX and a getY accessor method. But it's a way around it. Okay, the other thing that we need to talk about a little bit is Java inheritance. Java is an object-oriented language, so we can have type hierarchies. Here we've got a simple one, which is shape as superclass, 3 subclasses, triangle, square, and pentagon. Now, the problem that we have here is that we have no control over who can subclass from shape other than to make it final. If we make it final, we all know nobody can subclass it. But there's no way of controlling previously how to restrict who can actually subclass from that. So in JDK 15, we got the idea of sealed classes. Now what we can do is we can say public, and we have a new modifier, sealed, class, shape, and then we add a permits clause, which will define which subclasses are allowed for this particular class. So permits triangle, square, and pentagon. This is all good because now, if somebody comes along and says, oh, I really like that shape class, I want to subclass it into a circle, the compiler is going to go, no, you can't do that. Java is going to say class is not allowed to extend sealed class shape. It's not listed in the permits clause. So this allows you to create a sealed hierarchy for your classes. Now, the other thing that's important here is that all of the subclasses of your sealed class must explicitly state their inheritance capabilities. 3 different ways of doing that. First is to continue having a sealed class and provide another permits clause of further subclasses. So we can say sealed class triangle permits equilateral and isosceles. We could make the subclass final so that we can have no further subclassing of it. That's easy enough. And then we have the non-hyphen sealed class. This is where we're effectively turning off sealing so that we can have anybody subclassing, in this case, pentagon. This introduces an interesting thing that we're going to come back to a little bit more later on, which is the idea of contextual keywords. Because non-hyphen sealed, the first thing is it's the first hyphenated keyword in Java, but it's not a full reserved word. It's a contextual keyword because we can only treat it as a keyword when it's used in that specific place. There's a good reason for that, because I could create some code which said, I've got an integer called non, I've got an integer called sealed, and then I could say sealed equals non-hyphen sealed. But in that case, it's not a keyword, it's actually the subtraction of non minus sealed. Okay, so now let's get onto the pattern matching side of things. What do we have currently in Java? I'll deal with a couple of things that might happen in the future later on. The first thing that we need to think about here is the instance of operator. And obviously we use this a lot in our code. It allows us to take a reference to an object, and because of polymorphism in object-oriented programming, we can view that object as any of the types that it represents, meaning any of its specific type, any of the superclasses of that, and any of the interfaces that it or its superclasses implement. In order to determine exactly which of those we're specifically using, we can use the instance of operator. So we're all familiar with this, and we can do something like this. If obj instance of string, but then the problem is that we have to do an explicit assignment with a cast to another variable of that specific type. So we have string s equals cast it to a string obj. Now, this is one of those things where you think, well, why do we have to do that? Because if the compiler has determined that this is an instance of string, why can't we just treat it as a string within the body of that if statement? But that's the way that it works. So now in JDK 14, we have pattern matching for instance of. And again, going back to the definition I gave you at the beginning of what we're dealing with in terms of a pattern, what we've got for the predicate is the idea of obj instance of string. We're testing to see if the obj reference is a type string. That's our predicate. And then the pattern variable that we're going to use is s. If we do have a string, then in the true branch of that if statement, we can reference s as a string, and we can use it and determine the length of the string. We don't have to do the explicit assignment and cast that we would have had to do before. Now, again, sort of coming back to this, I was actually talking to James Gosling about this yesterday because I asked him, what he thought of the way that Java was going in the direction. And we got talking about pattern matching, and he said, well, yeah, but do you really need that extra variable? Because again, why can't we just say, well, if it's an instance of string, and then why not just use obj within the true branch? But this is the way that it actually works in the way that's been designed. Now, we can go a little bit further than that. So what we can now do is we can also say if obj instance of string s and s.length is greater than 0. We can do that because we know the way that the AND operator works is to always evaluate the left-hand side of the AND, and only if it equates to true do we evaluate the right-hand side. If it evaluates true, we know we have a string, so the scope of s will be valid as a string, and then we can test the length on the right-hand side. If we did that with an OR statement, that won't work, because clearly, again, we know how the OR operator works. We always evaluate the left-hand side first. Only if it equates to false do we evaluate the right-hand side. If it equates to false, we don't have a string, therefore the scope of S is not going to be valid, and we can't then test the length. Which sort of brings us to the idea of the scoping of our pattern variables. We have to sometimes be a little bit careful about that, because we could do something like this. We could say, invert the test and say, if not O instance of string S, return. And then after that, because we've inverted the test, the true branch is effectively everything after that, and so the scope of S is valid for the rest of the method. And that could be even after several hundred lines of code. We can still reference S, we can still use it, and call the length method on that. Which brings us to the definition of how we scope our pattern variables. Rather than using the way that we do for local variables, we use what's called flow scoping. If you look at the way that we scope local variables, we know that the scope is from wherever we declare that variable until the end of the block in which it's declared. Now that could be just a block in terms of braces, it could be a block for a for loop, a while loop, a do loop, or the whole method. But it's that scoping that we use. And the other important thing about local variables is they are subject to definite assignment, meaning that the compiler will check that at some point you give it a value, otherwise it will reject it. For pattern variables, they're also subject to definite assignment. They have to be assigned a value. And the scoping of a pattern variable is all the places where it has definite assignment. So wherever that variable actually has a value is where its scope is. So it is slightly different to the way that local variables work. It's not just in a block. It's within the places where those things are actually valid. So for example, we can do this, which we can't do with local variables. We can say if O instance of integer, and then use the variable num, else if O instance of float, and reuse the name num. We couldn't do that with a local variable, but we can do it with a pattern variable. And we would need flow scoping in order to do that. So it's only where the definite assignment for that variable is that it's actually its scoping exists. So as I say, slightly different to local variables. Yes, and so this is an interesting one. Puzzler for you. If I create a piece of code like this, so I create a new object reference S, and I assign to that a new instance of an object. And then I say if S, instance of string, and use S as my pattern variable, as well as the variable that refers to the object. If it is, I print out the length of the string. If it isn't, I print out no string. So let's have a show of hands. So who here thinks this will compile? Okay, a few people, probably be, okay. Who thinks it won't compile? Okay, most people think it won't compile. Anybody here think that it will both compile and not compile? Yes, so how does quantum superpositioning apply to code like this? Well, the answer is actually it will both compile and not compile. What do I mean by that? Well, if you try and compile this code with Java-C, it will not work, because obviously what it's going to complain about is the fact that the variable S has already been used. But if you run it in JShell, it will work. Bizarrely, and I literally have just cut and pasted from JShell onto the slide here, and I did check that with JDK 19 this still does exactly what I thought it did, and for some reason it quite happily allows you to reuse S even though you've used S to reference the object there. I have no idea why some people tell me it's a bug, but it doesn't seem to have been a bug that's been addressed in the last several versions of Java, so it's just an interesting aside there. Pattern matching for switch is the next thing we need to look at. So we already looked at switch statement and switch expressions earlier on. But the thing with the switch statement and the switch expression before was it was limited to the types that you can actually switch on. We were always dealing with things that were integral values, strings, or enumerations. What's happened now is we've extended that to allow type patterns to be used as well. In the same way that we have type pattern with instance of, now we can use it with the switch expression and statement. So what we can do here is we can say, right, let's have a type tester, pass in an object reference O, and then we'll switch on O. And now we can define a set of cases which allow us to test against the type, not just whether it matches a constant. First of those is null, and this is a new piece of syntax that's allowed the introduction of a special null case, so we can test that within the switch expression or the switch statement. This is really good because one of the problems we had before was that we always had to do the sort of test to see if we had a null outside of the switch. And that was kind of a bit fiddly because really a switch is just a multiple if then else. So why did we have to have an extra if outside of it? Now we can actually put that in. We can say case null. There is no pattern variable because null is null is null. There is no variation there. And so we can just print out we've got a null type. But then we can have pattern matching in terms of case string, give it a pattern variable s. So again, the pattern predicate is the case string, and the pattern variable is s. Print out the string afterwards. If we've got a color, we can do that. We can call the getRGB method on that. Now we can't have a case for a primitive because a primitive is not a type strictly in Java, but an array of primitives is. So we can have a case for int array, which we use the square brackets for, call that IA as the pattern variable, and then we can print out the length of the array afterwards. And of course, we can have our default there just to say, okay, it's not one of the others. So null is a little bit special in this case. As I said, they've introduced the idea of a special null case that you can test. But if you don't include that, then the compiler will effectively do it for you in order to maintain backwards compatibility with the way things have worked before. If we don't have the null case in our code, and we do this, so we switch on O, we've got string, color, int array, and default, what the compiler will effectively generate for us is to put in an extra case above that, which then throws a null pointer exception. So you get effectively the same way that the code works. It doesn't change anything for existing code that doesn't use an explicit null case. What's also interesting is that if you want to, you can include the null with the default. So you can do case null, comma, default, because now we have comma separated lists for our case. We can do case null, comma, default. And that's because they've introduced as well a special case for default. And I tested this because I thought to myself, I wonder if this will work. Yes, it does. You can do case default. Don't recommend it, but you can do it if you really want to. So there is a special case for default, a special case for null. Completeness. And again, I mentioned this when we talked about switch earlier on. What we need to do is look at a piece of code like this and say, okay, so we've got a type tester, we're switching on O, but what we've defined here is only two explicit cases, case string and case integer. What happens if I pass in a float or a short or something else? Well, you could argue that because there isn't a case for those, that you simply don't do anything, you drop through and you go past that case, past the switch and then carry on with the code. But that's not really the best way of doing it, I don't think. And obviously the designers of the feature also thought the same thing, which is let's ensure that every possible type is dealt with so that we can avoid the problem of ignoring something when we don't actually want to do that. What the compiler will then do is say, okay, in this case, it won't compile because you haven't got a complete set of types being dealt with. Now, in this case, the simple answer is to say add a default, because obviously if it's not an integer or a string, then we handle everything else through the default. The important thing there is that we don't have to have a default in every single situation. How can we get around that? Well, let's use the sealed class that we had earlier. So we had shape, which had three subclasses, triangle, square, and pentagon. We can use that in our shape test or type tester with shape, and now we can specify, okay, we're going to have case triangle, case square, case pentagon, case shape, and that will deal with every possible eventuality because we've dealt with every type that we could have there. It is a sealed type hierarchy, And so there are no other types that we can have there. A couple of you might be thinking, oh, hang on, what about the triangle where we subclassed it into an isosceles or an equilateral? But of course, that, through polymorphism, is still a triangle. So it would still be caught by the triangle case, and we didn't have to worry about that. So as long as we've got triangle, square, pentagon, shape, then we're catching everything, and it doesn't need a default. We can add a guarded pattern to this. And what we can do here in JDK 18 or earlier is to say case triangle T, in the same way that we did with the instance of operator earlier, we can say case triangle T and T.area greater than 25, it's a big triangle. But then we also have case triangle T below that, because again, we want to be complete, so we have a triangle T underneath there to deal with things that are not greater than 25. Technically, it wouldn't be a problem even if we didn't have the triangle there, because the shape would catch that at the bottom, but we add the triangle there. In this case, the guarded pattern syntax is primary pattern with an AND operator followed by a conditional AND expression. In JDK 19, they decided to change this, and they decided to change it to when. Not totally sure about this. But anyway, so what they said was, let's use, for a guarded pattern, rather than using the AND operator, let's say case triangle T when T.area greater than 25. It does make it a little bit more readable, I suppose, in terms of English, but it does create some problems. Okay, so the first thing is this only works for patterns. So you couldn't do case foo with a constant string when something else. That won't work. So it only can be used in patterns like this. Where when is important, because when is a contextual keyword. This is quite important because obviously, people might have used when as a variable name, and so we don't want to limit that use because it will break backwards compatibility. Let's assume that we create an abstract class called interrogator, and we will have 5 subclasses permitted from that, which are who, what, where, when, why. We'll also say that in the case of the when class, we'll make that final, and we'll add a method which is Boolean, and it's called when. Right. What we can then do is we can have a test question method, which takes an interrogator, and we can have some cases for that. So we'll have case what, and we'll print out what, and then case where, we'll print out where, case why, and then we'll have a default which says how. We can get quite ugly with this. So we could do, let's add 2 private methods, where and why. And then we can do case who, what, when, where, why. Because remember that when is a contextual keyword. So what we're saying is case who is the type, what is going to be the variable name, the pattern variable associated with the who instance, which is a bit wrong anyway, and then we'll use when as a guarded pattern. We'll test it using where, the method that we've declared lower, and then we'll also say we'll call why in the result that in the case that we have a true result there. But we can go one step further, and we can be really, really ugly, because we can also do case when. Because now what we're doing is we're saying in the case where we have a when type, we'll call that when, then we'll have when as the contextual keyword for our guarded pattern. We'll call the when method on the when reference, and then we'll call the when method that we've declared privately in that case. I don't recommend this. Definitely don't recommend this for production code, but it was just interesting to see just how far you can take this. Pattern dominance is also very important. Pattern dominance is also very important. Now, the order in which we put our cases. If we put the shape at the top of that list, what we're going to see is that shape is the superclass of triangle, square, and pentagon. So all of those classes are shapes, in which case we're going to match against that every time without doing anything else. That effectively makes triangle, square, and pentagon cases unreachable, so the compiler will not let you do that. It will give you an error and say, nope, you've actually made the rest of the cases unreachable. And that's good because clearly that's not what we want to do. So we have to make sure that we put the less specific types at the bottom and more specific types above there. Similarly, we have to be careful with our guarded patterns, because if we do the case triangle T first, it will always match, and so that becomes incorrect because we'll always match against the triangle first, regardless of what its size is. We'll never get to the point where we try and do the actual test on the area. Now, again, you see, you need to be a little bit careful that it doesn't always have to be the case that the guarded pattern goes before the unguarded pattern, because if we did something like this, which wouldn't really be very good, if you did triangle T when true, well, that just is the same as a triangle T, but technically, the compiler will reject that because we're hiding the code that is underneath, so it's dominating the unguarded pattern. So essentially, what the specification says is it is a compile time error for a label in a switch block to be dominated by an earlier label in that switch block. So you need to get the order right so that you've got your most specific and the guarded ones in the right order. Pattern matching instance of and records. Right, so we can pattern match against a record. Let's use a record like we had before, a point, double X, and double Y. Now what we could do is we could create a simple Pythagoras method, and we'll say pass in an object, and we say if O instance of point P. Our pattern that we're going to match against, our predicate is O instance of point, then we'll have a pattern variable P. In order to use the values within that record, we can call the accessor methods, and we can assign X to be P.X and Y to be P.Y, and then we can use that in terms of calculating the length of the hypotenuse. But we could do better than that. So this is where we see the idea of a deconstruction pattern. Introduced in JDK 19, the idea of record patterns. So it's deconstruction pattern, and interestingly, deconstruction patterns will only work with records. You can't use them with a non-record class. I did try it, and the compiler will reject it. So you can do this. You can say if O instance of point, but then give the definition of the point record with the parameters that are stored in there, double X and double Y, and that way you don't have to explicitly extract the values of X and Y and make the assignments. You can simply say print out hypotenuse and then do reference X times X, Y times Y. So you're getting access to those variables without you having to do the extraction. It's the compiler that's doing that for you. Patterns are composable. What do I mean by that? Well, let's define an interface called rectangle. Let's have our point that we had before. Let's also introduce an enumeration called color, red, green, blue. And then we'll have a couple of extra records. First one is a color point, which takes a point and a color. And then we'll have a record which is a color rectangle, which is color point top left, color point bottom right, and we'll say that that implements rectangle. What we can then do is we can say print the color of rectangle R, and we'll say if R instance of color rectangle, and of course we can deconstruct that by referencing color point top left, color point bottom right, and then we can print out the color by saying top left dot C. But of course we know that top left is also a record, so we can go one step further. We can say if R instance of color rectangle, and then we put the definition of the record color point, so point P, color C, and then color point BR, because we're not really interested in that, and then we just print out C. So we can compose the record patterns that we're using to get to exactly what we want to get to. But of course we know that point is also a record, so we can go one step further. And we can say print the top left X of that rectangle if our instance of color rectangle, color point, point, double X, double Y, color C, color point BR, and then print out just X. Now you might be looking at that and thinking, well, yeah, it's good, but it's kind of getting a bit unwieldy and a bit sort of complicated, which is where we can simplify things, because what we can do is we can use local variable type inference. Introduced in JDK 10, you can quite happily use this with your record patterns, composable record patterns, and that will allow you to do something like this. So you can now say our instance of color rectangle, color point, and then you just say var x, var y, var c, var br, and you don't care about what those types are. You'll let the compiler infer them for you, and then you just print out x as the value you actually want. So that does make life simpler. But what we could do is, in theory, if the language allowed us to, and hopefully it will at some point, is to use the idea of the underscore, the any pattern. As I say, I'm speculating about this as something which might, I'm told it might make it into JDK 20. We'll see. So we could then do this. We could say color rectangle, color point, var x, because that's the only thing we're actually interested in. We want to get the x value. But then for the other things, we don't care what they are, we don't care what their type is, but we need to reference the fact there is something there. So we just put an underscore, and that just says, right, there are fields there, but we don't care what their type is, we're not going to use them, we're not going to reference them. So we've got no interest in those, we just ignore them. Named record patterns. Okay, this is again where life gets kind of interesting. So let's create an interface called shared point, and we'll give that a Boolean method which is shared. You can see now why I'm not typing, because this would get all very messy if I was trying to type this at the same time. And we'll create two records, one called point2d. We'll give that a double x and double y. It implements shared point, so it's got an implementation of is shared, just returns true. Same thing for point 3d, but this time we'll give it a z-axis element and also implement is shared, shared point, and there it has a is shared method which returns true. Great. So now what we can do is we can use that with an unnamed record pattern, as we've seen before. In this case, we'll say case point2d, define the record structure as double x, double y, and print out the value of x. For our point 3d, we've got the extra z, and then we print out the value of z. And we've got a default so that we're sort of complete. Okay, so that's an unnamed record. What about if we want to actually use the record in some way? So now we can do case point2d, double x, double y, and now we have a pattern variable, p, which we're going to print out 2d, is it shared, and the value of x. Okay, that'll all work quite happily, no problem with that. However, what about when we do this? So now we'll add a guard to that, and we'll say case point2d, double x, double y, p, when p is shared, and then we print out p is shared and x. That will compile quite happily, there is no problem with that. What gets tricky and won't compile is when we go back to using when as a variable name. And if we do when is shared, this will not compile. This will give you the error that a colon or a arrow is expected. So the compiler gets confused about the fact that what we're actually doing is trying to add a guard to this rather than just a named pattern in this case. So also, if we add another when method to that, which is a Boolean that returns a Boolean, we could do this. We could say point2d double x double y when true in brackets. This is really where the compiler does get very confused, because of course, what do we actually mean by this? Do we mean that we're giving the name to the record, which is going to be when, or are we saying this is a guard where we're going to call the when method that we've declared privately with true? So yes, it won't compile, and the compiler complains about can't find the symbol when, which makes complete sense to me. Like what's going on? So anyway, so what they've said is that there's a bug raised about this, and the chances are that in JDK 20 they will remove the idea of named record patterns, so you won't be able to do this or anything like this in the future. Although again, there is still a lot of discussion about whether they should do that or not. There's definitely sort of pros and cons on both sides. Last thing to talk about is pattern matching for arrays. Now, this was something that was going to be included along with record patterns, but isn't actually now included in the JEP that defined that. it may come at some point in the future. So it's not part of what we're seeing at the moment. So this essentially is saying, in the same way we could have a deconstruction pattern for records, why shouldn't we do the same thing for an array? Here, what we're doing is we're saying if O instance of string array and, so we're giving it a guard there, and SA.length is greater than or equal to 2. Then what we can do is we can extract the value of the first element in the array, the value of the second element in the array, and then print out the concatenation of them. The idea is that you could then actually apply a pattern to that and a deconstruction pattern. So you could say if O instance of string, then you could say string S1, string S2, use the ellipsis to indicate that you're using var args, so there could be any number of elements after that, but there must be at least 2. Then you would print out the concatenation of S1 plus S2. As I say, this is not in the definition yet. I think there's still some things that need to be worked out about the way this works, especially in terms of like var args and the ellipsis and things like that. So was supposed to be part of JET 405, drop for now. So to summarize then, pattern matching is a powerful set of language constructs. And I think it's fair to say that it simplifies some tasks. Some tasks you can make look very ugly and more complicated than they need to be. But if you use it wisely, then you can reduce the amount of boilerplate code in terms of the way a lot of these things work. It is more declarative in the way that it works as well. There's also some interesting discussion around the way that, even though this looks a lot like sort of syntactic sugar, there are potential for optimizations at the JVM level in terms of how you run this code and make it code actually work better. Lots of features already there. Many of them are still in preview. So even up to like JDK 19, so record patterns are a preview feature, and there's a couple of others as well that are still previews. More to come. I think we'll see other stuff going on, and then maybe even yet more added later on. So that is it. So thank you very much. I do have 4 minutes, so if anybody's got a question, okay, yeah.
A couple of them. When you do a switch with the sealed class, how do you deal with null?
Right. So if you do a switch with a sealed class, how do you deal with null? Well, you can put the explicit case null in there.
But then if you don't put it, it's still exhausted. How is the
So yes. Yeah, so the question was, how do you deal with a case of null in a sealed class? I think the simple answer is it doesn't make any difference, because if you put the explicit case null in, then obviously you can deal with that. If you don't put it in, the compiler is going to insert it effectively as the first case and throw a null pointer exception.
If it is implicit, you just keep it there.
Yes, yeah. So if it's implicit, you could just keep it there. Yes.
Second question is, when you do decomposition, how is that you're obliged to put either the type of variable or the var? How do you just drop the type? Like you do in lab.
So the question is, if you use composable patterns and you use var.
Yeah, you're obliged to use either var
Yeah.
or the type of.
Yeah, so you can either use var or the explicit type. It doesn't matter. It just has to match against whatever you've got in terms of your record. Yeah.
You showed before that you can do when clause in cases, like for example, triangle T when T.area larger than 25, and then under it you have triangle T that works. What didn't work was like triangle T when true,
Yep.
triangle T. What happens when you do triangle T when T larger than 25, and then the other smaller than 25, and then don't have anything else?
Right. Okay. Yes. So. Yeah. So the question is, if we have the case triangle T when area greater than 25, and then case triangle T when area less than 25, what? Yeah, or equals. Well, remember that we've also got the case for shape. Well, if you didn't have the case for shape, you wouldn't be able to compile it because it wouldn't be complete. Because you could have an instance of shape, because shape wasn't abstract. So you could instantiate shape, and therefore it wouldn't match. If you pass the shape in.
It does fail if it's true, and so the more specific case covers the less specific case.
I'm not. Yeah, I think I would have to test that to see if you start using complicated guards, how clever the compiler can be to determine whether it's complete or not. Yes.
Everything above this line, everything below this line.
Yeah.
If you, is that enough, or do you need to specify anywhere else?
Yeah, I think I would have to test that one to see exactly what happened. Okay, I'm pretty much out of time now, so thank you very much.